Good day. So this chapter is all about communication tests and measurements. So we are going to introduce you to the wide range of special testing equipment and measurement procedures used in communication electronics. So if you are employed in communication electronics, your work will involve some form of testing and measurement. The work may be design, evaluation, installation, operation, servicing, repair, and maintenance or testing to specifications or standards. Voltage measurements. We all know that most common measurement obtained for most electronic equipment is voltage. This is particularly true for DC and low-frequency AC applications. In RF applications, voltage measurements may be important under some conditions, but power measurements are far more common at higher frequencies, particularly microwave. There are two basic ways to make AC voltage measurements in electronic equipment. One is to use an AC voltmeter, while the second method is to use an oscilloscope. Most conventional voltmeters can measure AC voltages from a few millivolts to several hundred volts. One of the most commonly used RF test instruments is the power meter. Power meters come in variety of sizes and configurations. One of the most popular is a small inline power meter designed to be inserted in the coaxial cable between a transmitter and an antenna. The meter is used to measure the transmitter output power supplied to the antenna. A short coaxial cable connects the transmitter output to the power meter, and the output of the power meter is connected to the antenna or dummy load. A more sophisticated power meter is the bench unit designed for laboratory or production line testing. Power meters may have either an analog readout meter or digital display. The dial or display is calibrated in milliwatts, watts, or kilowatts. The operation of a power meter is generally based on converting signal power to heat. Whenever current flows through a resistance, power is dissipated in the form of heat. As you can see in the figure, it is an example of the monomatch circuit. It uses a 50-ohm transmission line made with a microstrip on a small printed circuit board or the PCB. The center conductor is a segment labeled 2 in the schematic. On each side of the center conductor are narrower pickup loops labeled 1 and 3. An RF voltage proportional to the forward and reverse power is produced as the result of capacitive and inductive coupling with the center conductor. The voltage in segment 3 represents the forward power. It is rectified by diode D1 and filtered by C1 into a proportional DC voltage. This voltage is applied through multiplier resistors R3 and R5 to a meter whose scale is calibrated in watts of power. Power can also be measured indirectly. If the load impedance is known and resistive, you can measure the voltage across the load and then calculate the power with the formula P equals V squared over R. What is a dummy load? A dummy load is a resistor that is connected to the transmission line in place of the antenna to absorb the transmitter output power. When power is measured or other transmitter tests are done, it is usually desirable to disconnect the antenna so that the transmitter does not radiate and interfere with other stations on the same frequency. It is best that no radiation be released if the transmitter has a problem or does not meet the frequency or emission standards. The dummy load meets this requirement. The dummy load may be connected directly to the transmitter coaxial output connector, or it may be connected to it by a short piece of coaxial cable. Standing wave ratio meters. The standing wave ratio can be determined by calculation if the forward and reflected power values are known. In the figure shown, you can determine the standing wave ratio directly. In figure A, it shows a bridge standing wave ratio meter. A bridge is formed of precision non-inductive resistors and the antenna radiation resistance. In some SWR meters, resistors are replaced with a capacitive voltage divider. The meter is connected to measure the unbalance of the bridge. The transmitter is the AC power, while in Figure B, it shows the circuit rearranged so that the meter and one side of the bridge are grounded, thereby creating a better match to unbalanced coaxial transmission lines. The meter is a basic DC microammeter. Diode D1 rectifies the RF signal into a proportional direct current. If the radiation resistance of the antenna is 50 ohms, the bridge will be balanced and the meter reading will be 0. The meter is calibrated to display an SWR of 1. If the antenna radiation resistance is not 50 ohms, the bridge will be unbalanced and the meter will display a reading that is proportional to the degree of unbalance. The meter is calibrated in SWR values. Function generators. A function generator is a signal generator designed to generate sine waves, square waves, and triangular waves over a frequency range of approximately 0.001 Hz to about 3 MHz. By changing capacitor values and varying the charging current with a variable resistance, a wide range of frequencies can be developed. A function generator is one of the most flexible signal generators available. There are two basic types of RF signal generators. The first is a simple, inexpensive type that uses a variable frequency oscillator to generate RF signals in the 100 kHz to 500 MHz range. The second type is a frequency synthesized. These simple RF signal generators contain an output level control that can be used to adjust the signal to the desired level, from a few volts down to several millivolts. Some units contain built-in resistive step attenuators to reduce the signal level even further. Most frequency synthesized signal generators use a front panel keyboard. The desired frequency is entered with a keypad and displayed on a digital readout. As with other signal generators, the output level is fully variable. Frequency synthesized generators are available for frequencies into the 20 to 70 GHz range. Such generators are extremely expensive, but they may be required if precision measurement and testing are necessary. Sweep generator is a signal generator whose output frequency can be linearly varied over some specific range. Sweep generators have oscillators that can be frequency modulated, where a linear sawtooth voltage is used as a modulating signal. The resulting output waveform is a constant amplitude sine wave whose frequency increases from some lower limit to some upper limit. Sweep generators are normally used to provide a means of automatically varying the frequency over a narrow range to plot the frequency response of a filter or amplifier or to show the bandpass response curve of the tuned circuits in equipment such as receiver. The example of constant amplitude sine wave whose frequency increases from some lower limit to some upper limit is shown in the figure. A newer type of signal generator is called the arbitrary waveform generator. Arbitrary waveform generator uses digital techniques to generate almost any waveform. An arbitrary waveform generator stores binary values of a desired waveform in a memory. These binary words are fed sequentially to a digital to analog converter that produces a stepped approximation of the desired wave. The arbitrary waveform generator provides a fast and easy way to generate almost any signal shape. Because digital sampling techniques are used, the upper frequency limit of the output is usually below 10 GHz. Frequency counter is one of the most widely used communication test instruments. It measures the frequency of transmitters, local and carrier oscillators, frequency synthesizers, and other signal generating circuit or equipment. It is imperative that the frequency counter operate on its assigned frequency to ensure compliance with rules and regulations and to avoid interference with other services. A frequency counter displays the frequency of a signal on a decimal readout. What is a frequency? Frequency is a measure of the number of events or cycles of a signal that occur in a given time. The usual unit of frequency measurement is hertz or cycles per second. The time base generates a very precise that is used to open or enable the main gate for an accurate period of time to allow the input pulses to pass through the counter. All the techniques for measuring high frequencies involve a process that converts the high frequency to a proportional lower frequency that can be measured with conventional counting circuitry. This translation of the high frequency to the lower frequency is called the down conversion. Prescaling is a down conversion technique that involves the division of the input frequency by a factor that puts the resulting signal into the normal frequency range of the counter. It is important to realize that although prescaling permits the measurement of higher frequencies, it is not without its advantages, one which is loss of resolution. One digit of resolution is lost for each decade of prescaling incorporated. Spectrum analyzer. It is one of the most useful and popular communication test instruments. Its basic function is to display received signals in the frequency domain. Oscilloscopes are used to display signals in the time domain. The spectrum analyzer combines the display of an oscilloscope with the circuits that convert the signal to the individual frequency components dictated by Fourier analysis of the signal. The four basic techniques of spectrum analysis are bank of filters, swept filter, swept spectrum superheterodyne, and fast Fourier transform. All these methods do the same thing: decompose the input signal to its individual sine wave frequency components. Both analog and digital methods are used to implement each type. The most widely used are superheterodyne and fast Fourier transform. Superheterodynes are the most widely used RF spectrum analyzer. It consists of a broadband front end, a mixer, and a tunable local oscillator. The frequency range of the input is restricted to some upper limit by a low-pass filter in the input. While the fast Fourier transform method of spectrum analysis relies on the fast Fourier transform mathematical analysis, fast Fourier transform spectrum analyzers give a high-resolution display and are generally superior to all other types of spectrum analyzers. However, the upper frequency of the input signal is limited to frequencies in the tens of megahertz range. Network analyzer. It is a test instrument designed to analyze linear circuits, especially RF circuits. It is a combination instrument that contains a wide-range sweep sine wave generator and a CRT output that displays not only frequency plots, as does a spectrum analyzer, but also plots a phase shift versus frequency. How do engineers use network analyzers? It is used by engineers to determine the specific performance characteristics of a circuit they are designing, such as a filter, an amplifier, or a mixer. They are also useful in analyzing transmission lines and even individual components. The network analyzer applies a swept frequency sine wave and measures the circuit output. The resulting measurement data is then used to produce an output display such as an amplitude versus frequency plot, a phase shift versus frequency, or even a plot of complex impedance values on a Smith chart display. What are vector signal analyzers and generators? A vector signal generator is a variation of an arbitrary waveform generator. In some instruments, the signal may be generated at a lower intermediate frequency and then mixed by an up converter to the desired higher output frequency. Most vector signal generators are provided with pre-programmed signal formats for the most common wireless standards, while vector signal analyzer is an instrument designed to capture and provide a way to disassemble a signal to see its detail. A vector signal analyzer is similar to a spectrum analyzer but with more output options. It is useful in design to ensure that new circuitry meets the desired standards. It is also useful in troubleshooting to locate problems and standards variations. Field strength meters. One of the least expensive pieces of RF test equipment is the field strength meter. It is a portable device used for detecting the presence of RF signals near an antenna. The field strength meters are a sensitive detector for RF energy being radiated by a transmitter into an antenna. It provides a relative indication of the strength of the electromagnetic waves reaching the meter. The field strength meter is a vertical whip antenna, usually the telescoping type connected to a simple diode detector. Transmitter tests. Four main tests are made on most transmitters: tests of frequency, modulation, and power, and tests for any undesired output signal components such as harmonics and parasitic radiations. These tests and measurements are made for several reasons. First, any equipment that radiates a radio signal is governed by Federal Communications Commission rules and regulations. For a transmitter to meet its intended purpose, the Federal Communications Commission specifies frequency, power, and other measurements to which the equipment must comply. Second, the tests are normally made when the equipment is first installed to be sure that everything is working correctly. Third, such tests may be performed to troubleshoot equipment. If the equipment is not working properly, these tests are some of the first that should be made to help identify the trouble. Frequency measurement. The transmitter must operate on the assigned frequency to comply with Federal Communications Commission regulations and to ensure that the signal can be picked up by a receiver and tuned to that frequency. The output of a transmitter is measured directly to determine its frequency. The transmitted signal is independently picked up and its frequency measured on a frequency counter. Modulation tests. If AM is being used in the transmitter, you should measure the percentage of modulation. Well, of course, it is best to keep the percentage of modulation as close to 100 as possible to ensure maximum output power below 100 to prevent signal distortion and harmonic radiation. In FM or PM transmitters, you should measure the frequency deviation with modulation. The goal with FM is to keep the deviation within the specific range to prevent adjacent and channel interference. So the best way to measure AM is to use an oscilloscope and display the AM signal directly. Power measurements. So most transmitters have a tune-up procedure recommended by the manufacturer for adjusting each stage to produce maximum output power. The procedure for measuring the output power is to connect the transmitter output to an RF power meter and the dummy load. Most modern power meters measure both forward and reflected power, so standing wave ratio measurements are easier to make. It may be necessary to adjust the antenna or matching circuit to ensure maximum output power with minimum standing wave ratio. Harmonics and spurious output measurements. The common problem in transmitters is the radiation of undesirable harmonics or spurious signals. The output of the transmitter should be a pure signal at the carrier frequency with only those sideband components produced by the modulating signal. Another problem is that other spurious signals can be generated by transmitters. In high-power transmitters, particularly parasitic oscillations can occur. These are caused by the excitation of small tuned circuits whose components are those stray inductances and capacitances in the circuits or the transistors of the tubes involved. It may be possible to reduce the harmonic and spurious output content by making a minor transmitter tuning adjustment. Antenna and transmission line tests. If the transmitter is working correctly and the antenna has been properly designed, About the only test that needs to be made on the transmission line and antenna is for standing waves. It will tell you whether any further adjustments are necessary. If the standing wave ratio is high, you can usually tune the antenna to reduce it. You may also run into a transmission line problem. It may be open or short-circuited, which will show you up on a standing wave ratio test as infinite standing wave ratio. Receiver tests. The primary tests for receivers involve sensitivity and noise level. The greater the sensitivity of the receiver, the higher its gain and the better job it does for receiving very small signals. So as part of the sensitivity testing, the signal-to-noise ratio is also usually measured indirectly. The ability of a receiver to pick up weak signals is just as much a function of a receiver noise level as it is of overall receiver gain. The lower the noise level, the greater the ability of the receiver to detect weak signals. As part of an overall sensitivity check, some receiver manufacturers specify an audio power output level. Since receiver sensitivity measurements are usually made by measuring the speaker output voltage, power output can also be checked if desired.
Common communication test, receiver test, equipment required. To make sensitivity and noise measurements, the following equipment is necessary. Dual trace oscilloscope. The vertical frequency response is not too critical, for you will be viewing noise and audio frequency signals. RF signal generator. This generator provides an RF signal as a receiver operating frequency. It should have an output attenuator so that the signal as low as 1 microvolts or less can be set. This may indicate the needs of an external attenuator if the generator does not have built-in attenuator or output level adjustment. The generator must also have modulation capability, either AM or FM, depending upon the types of the receiver to be tested. RF voltmeter. The RF voltmeter is needed to measure the RF generator output voltage in some tests. Some higher quality RF generators have an RF voltmeter built in to aid in setting the output attenuator and the level controls. Frequency counter. A frequency counter capable of measuring the RF generator output frequency is needed. Multimeter. A multimeter is capable of measuring audio frequency. Voltage level is needed. Any analog or digital multimeter with AC measurement capability in the AF range can be used. Dummy loads. A dummy load is needed for the receiver antenna input for the noise test. This can be either a 50 or 75 ohms resistor attached to the appropriate coaxial input connector. A dummy load is needed for the speaker because the most noise and sensitivity tests are made with a maximum receiver gain including audio gain. It is not practical or desirable to leave the speaker connected. Most noise generated by the receiver occurs in the receiver's front end, primarily the RF amplifiers and the mixers. Careful attention is given to the design of both these circuits so that they contribute minimum noise, because noise is a totally random signal that is composite of varying frequency and varying amplitude signal. It is somewhat difficult to measure. However, the following procedure has to become a common and popular method that is easy to implement. Refer to the test setup shown. The antenna is removed from the receiver, and a dummy load of the correct impedance is used to replace it. A carbon composition resistor of 50 or 75 ohms can be used. The idea is to prevent the receiver from picking up any signals while maintaining the correct impedance. At the output of the receiver, the speaker is replaced with a dummy load. Most speakers have an output impedance of 4 or 8 ohms. Check the receiver specification and connect the appropriate value of resistor in place of the speaker. Be sure that the dummy loads resistors can withstand the output power. Finally, connect the dual trace oscilloscope across the dummy speaker. The same signal should be displayed on both channels of oscilloscope. the displayed signal with an amplified version of the noise produced by the receiver and amplified by all the stage between the antenna, input, and speaker. Follow this step-by-step procedure. 1. Turn on the receiver and turn it to the channel when no signal will be received. 2. Set the receiver volume control to minimum, rather, its maximum. If its receive has any type of RF or IF, gain control is to should to be to its maximum setting. 3. Set the oscilloscope input for the lower trace channel B to the ground. Most oscilloscope has a switch that allows to input to be set for AC measurements. DC measurements are ground. Grounding the channel B, input will be prevent any signals from being displayed. At this time, you will see the straight horizontal line for the lower trace. Adjust the lower trace so that it's lined up with one horizontal graticule line near to the bottom of oscilloscope screen. This will be provide a voltage measurement reference. Power output test. Sometimes it's necessary to measure the receiver's total power output capability. This is a good general test of all the receiver's circuits. If the receiver can supply the manufacturer's specify the maximum output power into the speaker with a given low RF signal level input, the receiver is operating correctly. The test setup for the power output test is shown at the figure. An RF signals generator for the correct frequency is used in a primary signal source. It must also be possible to modulate this generator with either AM or FM depending upon the type of receiver. Be sure to replace the speaker with a resistive load of an impedance equal to that of the speaker, such as 8 ohms. The damaged speaker load should also be able to output power of the receiver. Finally, connect an AC voltmeter across the speaker dummy loads. Turn on the receiver and set the volume control to the maximum. If the receiver has a variable RF or IF goal gain control, you must set it to the maximum setting also. At this time, any other receiver feature should be disabled. For example, in an FM receiver, the squall should be turned off or disabled. In an AM receiver, if a noise limiter is used, its too should be turned off. To begin the test, follow this procedure. 1. Set the RF generator output level to 1 mV. If the RF signal generator has built-in RF voltmeter, use it to make it this setting. Otherwise, an external RF voltmeter may be needed, as shown as figure. 2. Set the signal generator for modulation of appropriate type. If AM is used, set the percentage of modulation for 30. If FM is used, set the deviation for 3 kHz. In the most signal generators, the percentage of AM and the frequency deviation for FN are fixed. Refer to the signal generator specification to find out what these values are. 3. With everything appropriately adjusted, measure the AC voltage across the speaker dummy load. This will be an RMS reading. 4. To determine the receiver power output, use the standard power formula. P is equals to V squared over R. Quieting sensitivity test. In most cases, the sensitivity of the receiver is expressed in terms of the minimum RF voltage at the antenna terminals that will produce a specific audio output power level for most measurement factors in the effect of noise. The method of sensitivity measurement is determined according to the whether AM or FM is used, because the most modern radio communication equipment use frequency modulation. Measuring FM receiver sensitivity is illustrated. There are two basic methods, quieting and synod. The quieting method, measuring the amount of signal needed to reduce the output noise to 20 dB. As the signal levels increases, the noise level decreases until the limiter in the IF section begins to start their clipping action When this happens, the receiver output quiets, its output is silent and blank out the noise. The CNED test is a measure to the input signal voltage that will produce at least a 20 dB signal to noise ratio. The noise value includes any harmonics that are produced by the receiver circuits because of distortion. The test setup for receiver sensitivity measurement is shown at the figure. It contains of an RF signal generator, an RF voltmeter, a frequency counter, the receiver to be tested, and voltmeter to measure the output across the speaker dummy load. Blocking and third-order intercept test. As the spectrum has become more crowded and as modulation advanced have permitted higher speed per hertz of bandwidth, the potential of adjustment channel interference has significantly increased. To ensure minimum adjacent channel interference, receiver specifications have become tighter. This is especially true in cell phones, whose suites of tests must be passed with the receiver in order to meet any specification of the specific cell phone standards such as GCM or CDMA. Microwave test. Microwave tests are generally similar to those performed on standard transmitters and receivers. Transmitter measurements include output power, deviation, harmonics, and spurious signal as well as modulation. The techniques are similar but require the use of only those test instruments whose frequency response is in the desired microwave region. The same goes for receiver measurements and antenna transmission line tests. The procedures are generally the same, but the equipment is different. For example, with power measurement, its directional coupler is normally used as a transmitter output to reduce a signal to its proper level for measurement with a power meter. Data communication test. The tests for wireless data communication equipment are essentially the same as those for standard RF communication as described above. The only difference is the type of the modulation used to apply the binary signal to the carrier. FSK and its many variants, as well as PSK and spread spectrum, are the most widely used, especially FSK and PSK deviation and modulation meters are available to make these measurements. For data communication application in which binary signal are baseband or coaxial and twisted pair cables, such as in LANs, more conventional testing method may be used. For example, binary test pattern may be initiated in the transmitting equipment and signal viewed on the oscilloscope at the receiving end. Tests of the signal attenuation and wave shape can be made. Eye diagrams. A common method of analyzing the quality of binary data transmitted on a cable is to display what is known as eye diagram on a common oscilloscope. The eye diagram or pattern is a display of the individual bits overlapped with one another. The resulting output looks like an open eye. The shape of the pattern and the degree that the eye is open can be used to determine many things about the quality of the transmission. This figure shows a serial false train for alternating binary series to 1S that is applied to transmission line. The transmission line, either coaxial or twisted pair, is a low-pass filter and therefore it eliminates or at least greatly attenuates the higher frequency components in the false train. It also delays the signal. The result is that the signal is rounded and distorted as the end of the cable and input to the receiver. The longer the cable and the higher the bit rate, the greater is the distortion. The falses tends to blur into one another, causing what is called intersymbol interference. Intersymbol interference makes the voltage level for binary 1 and 0 closer together, one bit smearing or overlapping into the other. This makes the receiver's job or clearly distinguishing the binary 1 from the binary 0 more difficult. Furthermore, noise is usually picked up along the transmission path, making the received signals and poor representation of the original data signal. Pattern generators. A pattern generator is a device that produces fixed binary bit patterns in serial form to use a test signal in data communication systems. The pattern generation may generate a repeating ASCII code or any desired stream of 1S or 0S. Pattern generators are used to replace the actual source of data such as computer. Their output pattern can be changed to standard codes or message or may be programmable to some desired sequence. A pattern generation may be implemented in software at the sending computer. Bit error rate test. At the other end of the link, the pattern generator sequence is detected and compared to be known actual pattern or message sent. Any error in the comparison indicate errors. The instrument that detects the false pattern and compares its code bit error rate analyzer. It compares on a bit-by-bit basis and transmitted and receives data to point out very bit error made. It keeps track to the total number of bits, send the number of errors and occurs then the computers the BER by dividing the number of errors by the number of bits sent. The BER tester must, of course, know the exact pattern or the message sent by the pattern generator. TDR tests with an analyzer. Special data communication test instruments are also available. A popular instrument is the TDR tester, also known as cable analyzer or LAN meter. This instrument often handled and connected to the axial or twisted pair cable and is able to make tests and measurements, some of which are tests are open or short circuits and impedance anomalies and coaxial or twisted pair cables, measurement of cable length, capacitance and loop resistance, measurement of cable attenuation, tests for cable miswiring such as so-called split pairs. Protocol analyzers. The most sophisticated data communication test equipment is a protocol analyzer. Its purpose is to capture and analyze the data transmitted in a particular system. Most data communication systems transmit data in frames or packets that include preamble information such as sync, bit, or frames, start of headers code, addresses of source and destination, and its finite block of data, followed by the error detection code. A protocol analyzer can capture this frame, analyze them, and tell whether the system is operating properly. The analyzer will determine the specific protocol being captured and then indicate whether the data transmitted is following the protocol or whether there are error and transmission in formatting the frame. Fiber optic test equipment and measurements. A variety of special instruments are available for testing and measuring fiber optic systems. The most widely used for fiber optic instruments are the automatic splicer and the optical time domain reflectometer. Automatic splicer. Splicing fiber optic cable is a common occurrence in installing and maintaining fiber optic system. This operation can be accomplished with hand tools especially made for cutting, polishing, and splicing the cable. However, as the cable thickness has gotten finer, hand splicing has become more difficult than ever. It is very difficult to align and to cable ends perfectly before the splice is made. Optical time domain reflectometer, another essential instrument for fiber optic work, is optical TDR or OTDR. It is an oscilloscope-like device in LCD display and built-in microcomputer. Common problems. Many repairs can be made quickly and easily because they result from problems that occur on a regular basis. Some of the most common problems in communication equipment are power supply failures, cable and connector failures, and antenna trouble. Power supplies. All equipment is powered by some type of DC power supplies. If the power supply doesn't work, the equipment is completely inoperable. Therefore, one of the first things you should do is to check that the power supply is working. Cables and connector failures. Perhaps the most common failures point in any electronic system or equipment are the mechanical component. Connector and cables are mechanical and can be a weak link in electronic equipment. When it has been confirmed that the power supplies are operating correctly in equipment, the next step is to check the cable and connectors. Start by verifying the connectors and correctly attached. Another common problem is for the cable attached to the connector to break internally. Most of the time, the cable does not break completely, but one of the more wire in the cable may be broken while other remains attached. Antennas. Another common failure in communication system is the antenna. In most cases, antennas of portable equipment are fragile. A bad antenna is a common problem in handheld transceivers, cordless telephones, cellular telephones, and similar equipment. Troubleshooting methods. There are two basic approaches to troubleshooting transmitters, receivers, and other equipment: signal tracing and signal injection. Both methods work equally well and may often be used together to isolate a difficult problem. Signal tracing. A commonly used technique in troubleshooting communication equipment is called signal tracing. The idea is to use an oscilloscope of other signal detection device to follow a signal through a variation stage of the equipment. As long as signal is present and the correct amplitude and circuits are good, the point at which lose a signal in the equipment or in which the signal no longer conforms the specification is the location of the problem. In figure, it's a block diagram of dual conversion communication receiver. To troubleshoot this receiver, you need an RF signal generator to supply a low-level input to antenna terminals. Modulate the input with an audio signal, then using an oscilloscope, spectrum analyzer, or other instrument. Follow the signal through a various stage of the receiver. This procedure assumes that the power supply is working and other circuits with the correct DC voltage. Signal injection. Signal injection is somewhat similar to signal tracing. It is normally used with receivers. The process is to use signal generators of the correct output frequency to inject a signal into a various stage of the receiver and to check for the appropriate output response, usually to correct signal in the speaker. Signal injection is the opposite of signal tracing, where it starts at the speaker of the other output and works backward through a receiver from output to antenna. If the output of the audio, signal injection begins by testing the audio power output amplifiers. You inject a 1 kHz sine wave from the audio oscillator or the function generator in the input of the amplifiers. Follow the receiver documentation information with regards to how much signal should be present at the output of each stage. If an audio signal is heard, the speaker of the power amplifiers are okay. Then inject the audio signals in any other audio amplifiers stage back in the documentation circuit's output. Boundary scan and JTAG standards. Modern networking and communication equipment is made up primarily of digital ICs. These are large-scale devices made from surface mounting on the printed circuit board. It is difficult and sometimes not possible to access the pin on an IC, making signal tracing or injection worthless in troubleshooting. Realizing this, IC designers eventually figured out that a way not only to test a clip after it's made or packaged, but also to test equipment built in these clips. The method is called boundary scan. The purpose of boundary scan is to provide a way to observe test point inside the clip and not normally accessible and observe signals at IC pins inaccessible because of this surface mounting on PCB. And it's provide a way apply test signal to select point in a circuit that it then monitor the result. At figure shows, the boundary is scan circuitry that is built into many complex ICs. The logic circuitry to be tested is in the center and referred to as core logic. Surrounding the core is a series of the boundary scan cells. Each BSC is made up of pairs of flip-flops and some multiplexer that can receive input and store them or output their content when interrogated. The BSC flip-flops are also connected to form a large shift register, the boundary scan register. This register provides the basic storage unit for inputting and outputting data. The input and the output are serial. Serial data can input the register via the TDI line. Electromagnetic interference testing. A growing problem in electronic communication is electromagnetic interference, also known in earlier years as radio frequency interference and TV interference. Now, EMI is defined as many interference with a communication device by another electronic device. Since all electronic circuits and equipment emit some form of EMI, they are potentially sources of interference with sensitive communication devices such as cell phones, cordless phones, radio and TV sets, pagers, and wireless LANs. As the number of computers has increased, as more and more cell phones and other wireless devices have come into use, the EMI problem has become a major one. The problem is so great that a PCC has created interference standard that must be met by all electronic devices. Before any electronic equipment can be sold and used, it must be tested and certified by FCC to ensure that it does not emit radiation in excess of the allowed amount. Just as a strict rule and regulation have made design and manufacturing more difficult and have increased the cost of electronic product, but as a result has been fewer interference problems between electronic product and a reduction of disruption of their use. Reduction of electromagnetic interference. There are three basic techniques for reducing the level of EMI are grounding, shielding, and filtering. All these methods are used in designs of new equipment as well as reducing EMI in application in which the equipment is already deployed. Here is the brief summary of the techniques most often used. Grounding. A poor electrical ground often causes EMI. As you know, a ground is a common reference point for most, if not all, voltage in a circuit. These grounds show up in many different physical forms. It may be metal, chassis or rock, and metal frame of the building and water pipes. The best ground of an earth ground form when a long copper rod is driven into ground. Inside the equipment, the ground is formed with a PCB on which a component are mounted. The ground is usually the wide copper strip or in some cases a board copper ground plane formed in one side of PCB. Shielding. Shielding is a process of surrounding EMI emitting circuits or sensitive receiving circuits with a metal enclosure to prevent the radiation or pickup of signals. Often, just placing a metal plates between circuits or pieces of equipment to block radiation is sufficient to reduce or eliminate EMI. The metal reflects any radiated signals and can be actually absorbed some of the radiated energy. Filtering. The third method of EMI reduction is filtering. Filters allow desired signal to pass and undesired signal to be significantly reduced in level. Filters are not much help in curing radiation or signal coupling problems, but they are very effective way to deal with conducted EMI interference that is passed from the one circuit or piece of equipment to another by actual physical conduction over the cable or other connection. Typical decoupling circuits are shown in the figure. Instead of using a physical inductor, in series with a DC line, small cylindrical ferrite beads can be placed over a wire conductor to form a small inductance. These beads are widely used to high-frequency equipment. The bypass capacitor must have very low impedance. Even the RF signals, ceramic or mica capacitors, must be used. Any plastic dielectric or electrolytic capacitor used by decouplings must be accompanied by a parallel ceramic or mica to make filtering effective at the higher frequencies. Measurement of electromagnetic interference. The rule and regulation pertaining the EMI are given in the Code of Federal Regulation Title 47, Parts 15 and 18. Anyone working in a communication field should have copies of the code, which can be obtained from the government printing office. Essentially, these guidelines state the maximum signal strength level permitted for the certain types of equipment, the accepted level of radiation varying considerably depending upon the type of equipment, the environment in which it's used, and the frequency range. The FCC also distinguishes between international radiators, such as wireless LANs and other wireless units, and intentional radiators such as computers.